Okay. Let's talk about strain rate. Now, strain rate isn't it doesn't come up that often in geomechanics, or well, it's not completely true. I mean, anytime we do any kind of, we often call it plasticity, right? So if you think about a stress strain curve, I think I showed you guys one for a metal on the first day. I'm going to define a new writing app because this one screws up when my hand hits the screen. So if you think about a stress strain curve, like, we're taught in undergraduate that stress is, in one dimension, stress is equal to Young's modulus times strain, right? That just implies a linear relationship, right? But I showed you guys a stress strain curve for steel the other day, where the linear part was so small you could barely see it, right? It was like in the first 1% of strain, and then it went like that, right? So all of this is, in a steel, we call that plasticity, right? Because this is not recoverable deformation. Like once you strain it into this plastic zone, if you unload it, you have permanent strain. All right, so if you unload it, it will unload with the same elastic modulus, but you'll have this much permanent strain, right? And then if you reload it again, it'll start there and go back up, and then when it reaches there. So, and everybody who's ever played with a paper clip, paper clip, you bend it and it doesn't go back to the, if you bend it just a tiny amount, it springs back. That's elasticity, right? If you bend it too far, then it doesn't go back to where it was. That's plasticity, right? That causes that, okay? Now, who would believe me if I told you that a rock can flow plastically like that? Rocks are brittle materials, right? Yeah. You hit a rock with a hammer and it just breaks into a million pieces. So there's no plastic flow. That's true if you put a rock in an MTS machine and you just hydraulically load it from the top and you can visually inspect it. But is there ever a rock in the 2 miles in the ground that's like that? What's special about a rock that's 2 miles in the ground? It's confined, right? It's confined. Right? And so when you have confining pressure, and confining pressure under 2 miles under the ground is immense, right? When you have confining pressure, the rock it's not a brittle material. In fact, the more confining pressure you have, the more plasticity you'll observe. And I'll show you real data when we get to constituent modeling in a few weeks, right? But in the earth, in situ, rocks are not linear elastic, which basically says that everything you learn in undergraduate geomechanics is not correct, because in undergraduate geomechanics, all you considered was elasticity, right? Maybe you talked about plasticity, but you didn't solve any problems with that. You did talk about plasticity because you talked about like the Moore Coulomb failure criteria and other things, right? Which is it's like the first step towards plasticity. But yeah, rocks can, with high confining pressure, can flow like a metal. In fact, the elastic part will be so. I'll show you data where the elastic part is so small that you can't even see it. It looks like from the initial strain, it's flowing plastically. And we'll talk more about that later. But anyway, with respect, going back to strain rate, often when we solve plasticity problems, we solve them in rate form. And again, we'll see that. We'll talk about it later in the class. But and so that's when you need some notion of strain rate. Okay, and so it's not often that I used to work, I think I told you guys on the first day, I used to work at Sandia National Labs. And that's actually where I learned geomechanics, but in a completely different setting than what we'd look at in oil and gas production. What I did was I looked at weapons effects on rocks. So like projectile slamming into a mountain, what's going to happen, right? In fact, the type of weapons I looked at are called bunker busters. Have you ever heard of those type of weapons? So they're weapons that are designed to penetrate into the earth before they're, so that way you get like strong coupling to the earth with the blast, and they're meant to take out like bunkers, like hidden under the ground, right? And I didn't particularly like working on weapons, but the physics is really interesting. It's a really hard problem because even though you're not far under the ground in these applications, you have a kinetic energy projectile penetrating into the rock, and the pressures that are generated, it's a bullet, right? You're taking a rock that doesn't have a hole in it, and in a few milliseconds, you're making a hole and expanding that rock to move it out of the way for the projectile. You're pushing it out of the way. And in those regions near the projectile, you generate pressures that are even in excess of reservoir pressures. So the physics are the same. But in those applications, clearly, like there's also a strain rate effect. So you remember how I mentioned that rocks can get stronger as a function of pressure, confining pressure? They can also get stronger, and even metals get stronger as a function of strain rate. So typically for about typically when we talk about strain rates, we talk about like decades, like, because the units of strain rate, strain has no units, right? So strain rate is like 1 per second, right? And we typically talk about them like on a logarithmic scale. So like 10 to the 1, 10 to the 2, 10 to the 3. Talk about like decades of strain rate. And usually like a metal will get about 5% stronger for every decade of strain rate. So if you go from 10 to the 1, or 10 to 10 to the 2, 100 per second, the metal would typically be about 5% stronger. You go to 10 to the 3, 5% stronger, right? And these impact events are on the order of like 10 to the 3, 10 to the 4. So the metal could be, 10 to 20% stronger than it behaves if you just load it slowly, right? And again, some of these exact same things occur, with rocks. They have a rate effect. So, has anybody ever water skied? Nobody's ever water skied. There's a lot of lakes around here. You got to get somebody taking you water ski, or any kind of water sport, like even like on a tube or something, right? Right. So like if you just walked off the dock and just jump in the lake, it feels good, it doesn't hurt, right? But if you're going 40 miles an hour behind a boat and you fall and you slap the water, it hurts, right? That's a strain rate effect. It's different physics. In water, it's a surface tension effect. But in metals, it has to do with like a stacking up of plastic slip planes, like piling up against each other, which causes it to get stronger. And in rocks, it's even a different mechanism, right? And that basically, in rocks, the way rocks fail is like through essentially the initiation of microcracks. Like there's a lot of flaws in the rock, and you get this initiation of microcracks. But if you're loading it fast enough, a single crack can't grow fast enough to dissipate the energy, so it has to start branching. The cracks have to start branching and other things. And basically, it's like a piling up, if you will, of this microcracking process that can cause rocks to have this kind of rate effect, and other things too. So anyway, the point is, like, even though we probably we'll see it a little bit later in plasticity modeling, we're not talking typically in oil and gas applications, we're not talking about impact events where you have like a direct mechanism of strain rate, but we will need it in order to solve problems like this where there's some plasticity, and we will do that in this class. And the only way to solve these problems in any dimension higher than 1 is in a computer. Like you can't really solve these problems any other way. So that was a little aside. I don't know if y'all like those little anecdotal stories. Maybe I can even, when I'm looking for my stuff on my computer, I can show y'all some of the stuff we used to do at Sandia. Okay, so let's talk about what strain rate. All right, so let's just talk about our little dx. And what I'm going to do is I'm going to take the time derivative of that thing. Right? So I'm going to take the time derivative. It doesn't really make sense to talk about taking the time derivative of d big X, because by definition, d big X is in the reference configuration, right? It's at time t equal to 0, right? So that it doesn't, any derivative with respect to time of d big X is going to be 0. Okay. So we can swap the order of this. So we can say, like, we can move the ddt inside and leave the little d operator out. And so we can say dx dt okay. Well, what is all right, x is a position vector. It's a position vector in the current configuration. What's the time derivative of a position vector? Velocity, right? So we'll call it velocity. So we'll call this, that's v. So this is like dv. And just to be clear, v is in the current configuration, right? So it's a function of x1, x2, x3, and time. So using the chain rule, if I want to compute dv, or what I'll do is just write it for the single component, dvi, that is dvi dxj dxj. Everybody okay with that? Just chain rule. Right? This thing is called the velocity gradient. And we always use the symbol L. Remember, I told you before that we try to use, well, a lot of these symbols that we use are defined in the book by Malvern, the Continuum Mechanics Bible, the book by Malvern. And so, pretty much most people follow this notation, which is a good thing, right? Because it makes reading papers easier. You go, you can go read a paper, and you can, if you glance at it and you realize quickly that they're using common notation, the Malvern notation, then you don't always have to go back and read the nomenclature and stuff. You can just read the paper quickly because you realize they're just using the constant now Malvern nomenclature. So that the F, the L, all these things, the big X, the little x, all of that comes from Malvern. And I would say the vast majority of papers out there follow that. Okay? So that thing's called the velocity gradient. Okay, so let's look at how we can come up with the velocity gradient in terms of things that we've already derived. Okay, so let's start by taking the time derivative of the deformation gradient. And we'll do it in additional notation. Fij. So this is d dt. Remember, we had that equation earlier, and I pointed it out at the beginning of class that the deformation gradient can also be written partial little xi, partial big xj. So what I'll do, I'm going to call this, I'm going to switch back, I guess, to, maybe it wasn't necessary to write. I think maybe, yeah. So I'm going to switch back to matrix notation for a second, and I'm just going to call this F dot. Dot meaning the time derivative, right? It's a common symbol, right? So F dot oh, I know why I wrote this in additional notation. All right, so going back up here, what I want to do, I'm going to erase this real quick. All right, so I'll just say Fij dot, right? And I'm going to leave a little space, and again, we'll move the DDT inside. So this is like partial V, partial big X. Right? So it's like partial V I, partial big X J. Okay. And now what I'm going to do is I'm going to multiply on the right hand side by partial xj partial xk, right? This is the initial notation for matrix multiplication, right? So I have two free indices, so that the final there's something. If I multiply here, I have to multiply there too, right? So let me just go ahead and do that. Partial xj partial xk, all right? So the two free indices, I and k, so the final contracted tensor will have two components, second order tensor with indices over I and k. And then j repeats, so it's a summation, right? So this is a matrix product, right? Multiply two matrices together, okay? All right, what is this? Almost. That's the deformation gradient. What is this? The inverse of the deformation gradient, right? All right. So, but also we have partial big xj, partial big xj. We can cancel those terms. So we can cancel these terms. And then on the right-hand side, I'll write f dot. This thing is the deformation gradient. So F inverse equals what's left on the right after you cancel those terms, partial VI, partial XK. What is that? Velocity gradient. So in terms of the deformation gradient and its time derivatives, we can get the velocity gradient. So, you know, what you'll notice is that the deformation gradient just keeps coming up. It's like our most fundamental notion of deformation, right? And we can get the deformation gradient straight from the displacements and their derivatives, right? So, and that's what we're solving for. If we're going to write a computational code that we want to solve for the deformation of a structure, we're solving for the displacements, right? So if we know the displacements, we can compute the deformation gradient, right? And then if we know that, we can compute the velocity gradient. And this is kind of interesting because I don't know if I used this terminology, but the deformation gradient is like a two-point tensor. We call it two-point tensor because it takes things from the reference configuration into the current configuration, right? Goes in between. But this thing lives totally in the current configuration. So it's like you can start with something that's in the middle and end up with something that's totally in the current configuration. Yeah.
I have a question regarding the time derivative of the velocity gradient.
This thing?
Yes.
So all I did was, in differentiation, you can swap the order, right? So I just moved the DDT in. You can imagine I wrote it like this. Right? I just switched the order of differentiation. This is velocity.
Oh, sorry, that one is the dx or dv.
Do what?
Dx. That's the t bracket. Is it dx or dv?
This? That's an X. Sorry, yeah, sorry. Better? Yeah. I mean, you can also see it there.
Okay.
It comes from the deformation. We're just taking the time derivative of the deformation gradient. Okay.
I have a question.
Sure.
Like you said, velocity gradient only resides in the current configuration, but it's like right from it has deformation gradient, like it's equal to inverse of deformation gradient. But deformation gradient is somewhere in between, like both the configurations. So don't you think velocity gradient indirectly depends on both these configurations? Like in terms of like imagining this in potato diagrams.
Yeah, and you can actually in Malvern, I think it's on page 146 in Malvern, he does derive the velocity gradient in the exact same way that we derived the deformation gradient, by basically just drawing velocity vectors instead of displacement vectors and doing a Taylor series expansion and all of that. But I mean, just in terms of, this is the velocity gradient, right? That's the position in the current configuration, and this is the velocity in the current configuration. Right? So this lives in the current configuration for sure.